Hello again. Let's continue with hardware solutions. As we have already stated, many modern computer systems provide special hardware instructions that allow us to test and modify the content of a word or to swap the contents of two words automatically. That is, as one uninterruptible unit. We can use these special instructions to solve the critical section problem in a relatively simple manner. But these hardware instructions are specific to machine. So rather than discussing one specific instructions for one specific machine, one specific hardware, we are going to create an abstraction with the main concepts behind these types of instructions. So we have two basic instruction set which can be described as hardware instructions on this manner. We have test and set instruction, and as a second one, we have compare and swap instruction. Here, let's start with test and set. The definition of the atomic test and set instruction is here. So this is a Boolean instruction. It gets the address of another Boolean set and returns the value of this local instruction. So the important characteristics of this instruction is that is executed atomically. Thus, if two test and set instructions are executed simultaneously, each on a different core, they will be executed sequentially in some arbitrary order. If the hardware supports the test and set instruction, then we can implement mutual exclusion by declaring a Boolean variable log initialized to false. The structure of process I in this case can be described as in this figure. So we have a loop here, but instead of directly setting the value of this Boolean variable, we are using the test and set function. So we can initialize a variable log to false. So if it's false, we are going to do nothing. And if it's true, we can enter the critical section. The second one is compare and swap. The compare and swap instruction, just like the test and set instruction, operates on two words atomically, but use a different mechanisms that is based on swapping the content of two words. The compare and swap instruction operates on three operands as shown in this figure. We have 1, 2, and 3 operands. The operand value is set to new value. We have value and new value. We are going to set value as new value. Regardless, the compare and swap always returns the original value of the variable value. So here, as you can see, we are assigning the value to a temporary variable, and then we are setting value to new value if the value is expected. So actually we are making a compare here. For that reason it's called as compare and swap. If the value equals the expected value, then we are going to set new value as our value. But in every case, we are going to return the original value of our, let's say, this variable. Okay, we can change or we can set the value as new value or not based on the comparison, but in every case, we are going to return the original value. So the important characteristics of this instruction is that is executed atomically again. Thus, if two compare and swap instructions are executed simultaneously, again each on a different core, they will be executed sequentially in some arbitrary order. Here again, we have the solution using compare and swap function. Mutual exclusion using compare and swap can be provided as in this figure. A global variable log, again, we have to define a global variable log similar to test and set function, test and set solution. And we are going to initialize that log to 0. The first process that invokes compare and swap will set log to 1. So actually this is our compare and set function. This is value, this is expected value, and this is the new value. So in the compare and swap function, if the value of log is 0, we are going to set it, we are going to swap it as 1. So based on that, in every case, we are going to get the value of original value of log. So if it's not 0, we are going to do nothing. If it's 0, we can execute our critical section. If it's not 0, we can execute our critical section. And then after the critical section on the exit phase, we have to set the log 0 again. So again, the first process that invokes compare and swap will set to log to 1. So it will then enter its critical section because the original value of log was equal to the expected value, which is 0. Subsequent calls to compare and swap will not succeed because log now is not equal to the expected value of 0. When a process exits its critical section, it sets log back to 0, which allows another process to enter its critical section. So this structure again can be defined using this definition, this solution. Although this algorithm satisfies the mutual exclusion requirement, it does not satisfy the bounded weighting requirement. Of course, we can present different algorithms using the compare and swap instruction that satisfy all the critical section requirements, but we will pass it here. In this solution, we are just considering the mutual exclusion requirement. So we have instructions such as test and set and compare and swap, and then we have atomic instructions. Atomic instructions are hardware solutions and is generally hidden from application developers. Details describing the implementation of the atomic test and set and compare and swap instructions are discussed more fully in books on computer architecture because actually they are hidden from us. But it's still good to know how atomic test and set and compare and swap instructions works. Typically, the compare and swap instruction is not used directly to provide mutual exclusion. Rather, it's used as a basic building block for constructing other tools that solve the critical section problem. One such tool is an atomic variable, which provides atomic operations on basic data types such as integers and booleans. We know from previous sections that incrementing or decrementing an integer value may produce a race condition. Atomic variables can be used to ensure mutual exclusion in situations where there may be a data race on let's say, in a single variable while it's being updated, as when a computer is incremented. Most systems that support atomic variables provide spatial atomic data types as well as functions for accessing and manipulating atomic variables. These functions are often implemented using compare and swap operations. As an example, let sequence here be an atomic variable and let increment here be the operation on the atomic variable sequence. The command increment sequence ensures sequence is incremented without any interruption. So the increment function here can be implemented using compare and swap operation like that. It's important to note that although atomic variables provide atomic updates, they do not entirely solve the race condition in all circumstances. Atomic variables are commonly used in operating systems as well as concurrent applications, although their use is often limited to single updates of shared data as counters and sequence generators. So in the following sections, we are going to explore more robust tools that address race condition in generalized situations. But again, it's good to know that using the hardware instructions such as compare and swap, we can use atomic variables to prevent race conditions on data in specific circumstances. As we mentioned already, the hardware-based solutions is the critical section problem are complicated as well as generally inaccessible to application programmers. As an application programmer, it's hard to use hardware-based solutions because you have to know the details of computer architecture, you have to know the details of that specific machine. So instead of that, we can use some sophisticated problems instead of directly try to using hardware-based solutions. So operating system designers build higher level, not high level, but higher level software tools to solve the critical section problem. So instead of using that hardware solutions, we can try to use that sophisticated or higher level software tools which are provided by operating system, not the hardware itself. The simplest of these tools is the mutex log. In fact, the term mutex is the short for mutual exclusion. So instead of mutual exclusion, we can use mutex word. So the simplest tool can be provided by operating system designers to solve critical section problem is mutex logs. We use the mutex logs to protect critical sections and thus prevent race conditions. That is, a process must occur the log before entering its critical section. It releases the log when it exits the critical section. So the occur function occurs the log and the release function releases the log. The mutex log has actually a Boolean variable available whose value indicates if the log is available or not. We have a log which is a Boolean variable, so based on the value of that, we can easily understand that if the log is available or not. If the log is available, we can occur the log. If I can occur the log, I can enter my critical section. And after my critical section, I have to release the log because other processes can try to exit their enter their own critical sections. So if the log is available, a call to occur succeeds and the log is then considered unavailable to other processes. A process that attempts to occur an unavailable log is blocked until the log is released by its owner. Calls to occur or release must be performed automatically. This part is important. These calls must be atomic. So mutex locks can be implemented using compare and swap operations we already described. But on a higher level, operating system designers is going to use that compare and swap functions to create mutex locks to us. So we are going to just use occur or release functions instead of using directly hardware solutions. But we have a disadvantage here. The main disadvantage of the mutex is that it requires busy waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the call to occur, because other processes wants to enter their critical sections, they want to occur the lock, but the lock is not available. So it's called as a spin lock, because that processes has to loop continuously until occurring the lock. The type of mutex lock we have been describing is also called a spin lock for that reason, because the process spins while waiting for the lock to become available. So this is the main disadvantage of mutex locks. Here is the solution. The occur function occurs the lock, and the release function release the lock as illustrated here. So we have a lock. Lock is actually a mutex provided by the operating system. Before they entering the critical section, the process try to occur lock. If it can occur, it can enter its critical section, and then it has to release the mutex lock, because other processes can try to enter their own critical section. So we have to occur the lock. After the critical section, we have to release the lock. For that reason, it's called as a higher level solution. Instead of knowing the details of the hardware specific compare and swap functions, compare and swap instructions, we can directly use the mutex locks provided by the operating system. Mutex locks, as we mentioned, are generally considered the simplest of synchronization tools. In this section, we examine a more robust tool that can behave similarly to a mutex lock, but can also provide more sophisticated ways for processes to synchronize their activities. A semaphore is actually an integer variable that, apart from initialization, is accessed only through two standard atomic operations, wait and signal. So actually, this is the main difference between semaphores and mutexes. On the mutexes, mutex lock is a Boolean variable. So you can actually, the lock can be available or unavailable, just two options. But on semaphores, the semaphore S is an integer variable. So using the wait and signal events, you can change the value of S. You don't need to use just two options. It's an integer, so you can increase or decrease the value of S. So here is the definition of wait. While S is less than 0, you have to wait, because S is less than 0 means semaphore is unavailable. So you don't have any resources to use. But if it's not, if it's greater than 0, you can use one semaphore. You can use one resource. So if you use one resource, you have to decrease the value of S. And this is the definition of the signal operation. So after using your S, after using your semaphore, basically that means after your critical section, you have to signal S, which is going to increase the value of S. So you can consider wait and signal as occur and release. So here we are going to trying to occur the lock similar to mutex logs, but in this case we have more than one lock because it's an integer value. Let's assume that the value of S is 3. So if it's greater than 0, that means we can get one of that locks. Okay, so after the critical section, we have to signal semaphore. So it can be considered as the release function on the mutexes. So that means, okay, I use that source, I don't need it anymore, so I'm going to releasing it. That's going to increase the value of S in here. So all modifications to the integer value of the semaphore in the wait and signal operations must be executed atomically. Actually, it's very important on here. So this function has to be executed atomically. That is, when one process modifies the semaphore value, no other processes can simultaneously modify that same semaphore value. In addition, in the case of wait S, the testing of the integer value of S is less than 0, as well as its possible modification S minus minus here, must be executed without any interruption. Because, okay, I'm going to check the value and then I'm going to decrease the value. So this operation must be executed without any interruption. So we shall see how these operations can be implemented, but first let's see how semaphores can be used. Operating systems often distinguish between counting and binary semaphores. The value of a counting semaphore can range over an unrestricted domain. The value of binary semaphore can range only between 0 and 1. So for that reason, actually, binary semaphores behave similarly to mutex logs. So binary semaphore in that manner means mutex log. So when we say semaphore, generally we consider counting semaphores. So in fact, on systems that do not provide mutex logs, binary semaphores can be used mutex logs instead for providing mutual exclusion. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. It's not just a single lock. You have more than one resources and you are going to initialize the number of resources available as your S. Each process that wishes to use that resource perform a wait operation on that semaphore, thereby decrementing the value of the count of S. When a process releases a resource, it performs a signal operation. So that means it's going to increase the value of S. When the count for the semaphore goes to 0, that means actually all resources are being used. After that, processes that wish to use a resource will block until the count becomes greater than 0. So that means it has to wait until another process release actually signal the S. Here is an example. So for example, consider two concurrently running process 1 with a statement S1 and process 2 with a statement S2. Suppose we require that S2 be executed only after S1 has completed. We can implement this scheme readily by letting P1 and P2 share a common semaphore initialized to 0. We have a semaphore, we are going to initialize it to 0. Okay, the name is mutex, but actually it's a semaphore in this example. In process P1, we insert the statements S1 signal sync here. S1 signal sync. In process P2, we insert the statements wait sync 2. Because sync is initialized to 0, P2 will execute as 2 only after P1 has invoked signal sync, which is after statement S1 has been executed. So it's 0, so P2 has to wait until the value is greater than 0. And that means, first of all, P1 has to signal that semaphore to increase the value from 0 to 1. Only after that the P2 can execute the statement S2. So actually it's very similar to a memory barrier, but instead of using the memory specifications, you can directly use semaphores provided by operating system, and using that semaphore system as a mutual exclusion scheme, you can directly guarantee that S2 will be executed after S1. Okay, please remember the implementation of mutex logs. We described them. They suffers from busy waiting. The definitions of the wait and signal semaphore operations just described present the same problem, because on the wait function, on the wait call, you have to wait until the value of semaphore is greater than 0. So still there is a busy waiting condition on that point. To overcome this problem, we can modify the definition of the wait and signal operations as follows. When a process executes the wait operation and finds that the semaphore value is not positive, it must wait. However, rather than engaging in busy waiting, the process can suspend itself. Instead of waiting on a busy state, it can suspend itself. The suspend operation places a process into a waiting queue associated with the semaphore, and the state of the process is switched to waiting state. Instead of on the running state or ready state, we are going to change the state of that process to waiting state. We are going to suspend that process. Then control is transferred to the CPU scheduler, which selects another process to execute. So instead of keeping busy that CPU, we can suspend that process, because actually that resource, that semaphore resource, is not available for that point, because for that reason we don't need to keep busy that CPU for that process, because basically it's not going to make any progress. So in that case, we are going to suspend that process so CPU scheduler can execute another process instead of that busy one. A process that's suspended waiting on a semaphore S should be restarted when some other process executes a signal operation. The process is restarted by a wake-up operation, which changes the process from the waiting state to the ready state, because okay, now we have resources which you wanted to execute, you want to progress. So now you can wake up and use that resources. The process then placed in the ready queue. The CPU may or may not be switched from the running process to the newly ready process, depending on the CPU scheduling algorithm. But in some point, based on the algorithm, that process will be executed again. So we have two operations, block and wake up. If the semaphore is not available, instead of busy waiting, we are going to block, or we are going to suspend the process. And if another process signals the semaphore, that means, okay, now we have resources that process needs, and we can wake up that process. So basically that means we are going to move that process from waiting queue to the ready queue. Sorry, again, there's a problem with my monitor. Okay, to implement semaphores under this definition, we define a semaphore like that. Each semaphore has an integer value and a list of processes list. In the first example, we defined a semaphore just as a single integer, but in this case, instead of just a single integer, we are going to define our semaphore with an integer value and a list of processes, because we are going to keep the suspended processes on that list. When a process must wait on a semaphore, it's added to the list of processes. A signal operation removes one process from that list of waiting processes and awakes that process. Okay, because we are going to suspend some processes, but we have to store the information of that suspended processes because we are going to wake up that processes when a semaphore is signaled. Here is the implementation. Now, the wait semaphore operation can be defined like that, as the value of s will be decreased, but if s value is less than 0, instead of just busy waiting, we are going to add that process to our process list and sleep that process, actually suspend that process. And the signal semaphore can be described like that. Again, we are going to increase the value of semaphore, okay, but if the value of s is less than 0, that means this one is the first value, first resource released. So some of the processes can be waiting for that. So in that case, we are going to remove a process, just one process from S list, and we are going to wake up that process so it can use the resource now. So the sleep operation suspends the process that invokes it, and the wake up operation resumes the execution of a suspended process P from our lists. So these two operations are provided by the operating system as a basic system call. Your operating system has to provide these mechanisms. If you have actually, it has to provide some mechanisms for mutex and semaphores, and it has to provide that wait and signal functions, or if it has provide release and occur functions to you as simple, actually basic system calls, so you can use that calls as an application programmer. We have another solution. We have mutexes, we have semaphores. Semaphores can be binary semaphores or counting semaphores. Also, we have monitors. Although semaphores provide a convenient and effective mechanism for process synchronization, using them incorrectly can result in timing errors that are difficult to detect. Unfortunately, such timing errors can still occur when you use mutex logs or semaphores. That various type of errors can be generated easily when programmers use semaphores or mutex logs incorrectly to solve the critical section problem. One strategy for dealing with such errors is to incorporate simple synchronization tools as high-level language constructs. We have one fundamental high-level synchronization construct, which is called as monitor. An abstract data type, or ADT, encapsulates data with a set of functions to operate on that data are independent of any specific implementation of ADT. A monitor type is an ADT, or abstract data type, that includes a set of programmer-defined operations that are provided with mutual exclusion within the monitor. You can find detailed information about monitors on our textbooks, but I'm not going to give more details because it's a high-level language tool. On C programming language, we cannot use monitors because actually the basic systems basic language cannot provide that data types, basically. For that reason, we don't have monitors on POSIX or Winter2 API. So I'm not going to give more details about monitors, but it's good to know that, okay, distinguish between bootexes and semaphores. We have monitors too, and if you need any detailed information, you can take a look at our textbook. One consequence of using synchronization tools to coordinate access to critical section is the possibility that a process attempting to enter its critical section will wait indefinitely. So remember from the previous parts, we outlined 3 criteria that solutions to the critical section problem must satisfy. Indefinite waiting violates 2 of these, the progress and bounded waiting criteria. If one of your process is waiting indefinitely, that means it's not progressing. Also, you had not provided a bounded waiting time for that process. So liveness refers to a set of properties that a system must satisfy to ensure that process make progress during their execution lifecycle. A process waiting indefinitely under the circumstances just described is an example of liveness failure. The implementation of a semaphore with a waiting queue may result in a situation where 2 or more processes are waiting indefinitely for an event that can be caused on only by one of the waiting processes. The event in question is the execution of a signal operation. When such a state is reached, these processes are said to be deadlocked. To illustrate this, consider a system consisting of 2 processes, P0 and P1, each accessing 2 semaphores, S and Q, set to the value 1. Suppose that P0 executes wait S, then P1 executes wait Q. When P0 executes wait Q, it must wait until P1 executes signal Q. Similarly, when P1 executes waits S, it must wait until P0 executes signal S. Since the signal operations cannot be executed, P0 and P1 are deadlocked. They cannot continue their progress. P0 is waiting for P1, P1 is waiting for P0. So this is an example of deadlock. Other forms of deadlocks can be described as starvation, which is indefinite blocking. A process may never be removed from the semaphore queue in which it's suspended, and priority inversion, scheduling problem when lower priority process holds a lock needed by higher priority processes. So it can be solved using a priority inheritance protocol. Again, you can take a look at our textbook to get the details about priority inheritance protocol, but that's it for this week for us. So we discussed some synchronization tools. We started with Peterson's solution, which is a software solution, but then we realized that there is some problems on Peterson solutions. We cannot directly use Peterson solutions on modern architectures because we need some hardware support to create atomic operations. So in the next point, we discussed the hardware instructions such as test and set and compare and swap. Using test and set and compare and swap operations, we can create atomic chains on atomic variables. But these are just concepts that can be changed based on the specific hardwares. So as an application programmer, it's hard to understand every details on different hardwares. For that reason, operating systems has to provide some mechanisms to solve critical section problems. Of course, they have to use the hardware solutions such as compare and swap, but actually, again, they're going to create an interface between hardware and the application developer. As an application developer, you can use operating system calls to create or solve critical section problems, which are mutexes, semaphores, and monitors. On mutexes, actually, you have just a single lock. You can accrue that lock or release that one. So we have, actually, it's very simple, but we have a problem on mutexes. We can get a busy waiting if you use just mutexes. So for that reason, we can use semaphores. On semaphores, instead of just a binary value, binary lock, we can use a counting resources. Based on the number of your available resources, you can set the value of your S or semaphore, and you can decrease the value if someone waits on semaphore, or you can increase the value if some process signals that semaphore. Also, you can solve the busy waiting problem using semaphores. If a process has to wait until an available semaphore, you can suspend that process, and you can store the information of that process on a list. When another process signals that semaphore, that means, okay, now we have an available resource, so we can get one of the process from our list and wake up that process. So basically, that means we can solve busy waiting problem on the mutexes. Also, we have monitors. On Java side, we can use monitors, but on the POSIX and Win32 side, we don't have direct monitor solutions. But again, it's good to know that higher level languages can provide some abstract data types to solve critical section problem. And that is it for this chapter. Any question? Sorusu olan var mı? Yok sanırım. O zaman bir sonraki derste görüşmek üzere. Senkronizasyon araçlarından bahsettik. Bir sonraki derste bu senkronizasyon araçlarını kullanarak iyi bilinen diyeyim senkronizasyon problemlerine nasıl çözümler üretebiliriz, bunlardan bahsedeceğiz. Aslında bunları benchmark problemleri olarak da düşünebiliriz. Temel problemler var. Bu problemleri elimizdeki araçlarla nasıl çözebiliriz, nasıl çözümler üretebiliriz, bunlar hakkında konuşacağız. Önümüzdeki derse kadar görüşmek üzere. Hoşça kalın. Kendinize iyi bakın.